For the members of the public who are joining us on the line, the meeting will start at 7 o'clock p.m. Mountain Time, so in just a few moments. We are still waiting for a couple of our panelists to join, and we will be getting them linked in just momentarily here. We are also doing a test of the sound system, so if you'll hear some ambient sound, it's just that we're testing the sound system. So, Kara, if you turn your microphone on, and your camera on. Brian, when you're in, if you turn your camera on, we'll be able to see you. Kara, if you'd like to speak into your microphone, we can do a quick level. Hello? You still need to project your voice. Hello? There you go. Okay. Perfect. And Brian, if you're able to check your microphone.
Hello? Hello? I don't know if I'm on Zoom yet. It's not working.
I'll just remute the lines. For the members of the public who are joining us for our 7 o'clock Cold Spring Creek Debris Flow Mitigation Project Information Meeting, we will be underway shortly. We are just waiting for one of our panelists to arrive, and we will complete a quick check on the audio system before we begin, but we will be underway shortly. Dr. Jakob, I can see that you have now joined us. I see that you're disconnecting to the audio. It's Laurie Duchek from the Regional District here. Just wondering if you're able to hear us okay, and if you could just speak into your microphone so we're able to confirm that we can hear you as well.
I can hear you well, thank you.
Perfect, thank you. So we will be getting underway shortly. We're just getting a couple more people added here, and we will begin in just a few moments' time.
Sounds good.
Dr. Jakob, just before the meeting begins, if I could get you to mute your line until your presentation, it'll help reduce the ambient sound in the background on the video here.
Certainly will.
And for members of the public who are joining us, we will be underway shortly. If you do need to ask a question in the Q&A section, Director Clovechok will go over the process for that. And we will be underway in just a few moments. We're just getting one more person hooked up here to the video. For members of the public who are joining us for the Cold Spring Creek information meeting, we are just getting one more person connected here to the video, and we will be underway in a couple of moments' time. We'll turn things over to Director Clovechok shortly. Thank you for your patience. Thank you for your patience, everyone. We will be underway shortly. We're just getting one more person connected to the system here and are having just a little bit of difficulty. We appreciate your patience, and we will be underway momentarily. Thank you for your patience, everyone. We are going to proceed, and I will turn things over to Director Clovechok. If I could please have you unmute your microphone before beginning.
Thank you, Laurie. Good evening, everyone. Before we get started, I'd like to acknowledge that today I'm meeting with you on the traditional lands of the Ktunaxa and Secwepemc peoples. As you likely know, at the October board meeting, the RDEK received the updated hazard assessment on Cold Spring Creek as part of the work being done to begin phase 1 of the Cold Spring Creek debris flow mitigation project. We felt that it was important to get this information out to the community and ensure that property owners and residents know how to continue to receive information about the project and debris flow mitigation infrastructure within Fairmont moving forward. As you can imagine, pulling together a traditional meeting with all of us together in one room is not possible at this time. However, we are very grateful that the engineering consultants and all of you are able to join us virtually today or this evening. We also have a few people, this afternoon we had a meeting as well. It's exactly the same content. And we had a few people that were able to join us at the Columbia Valley Center, in addition to having some RDEK staff on site. But joining us for this session, either here online. We have our engineering consultants, Dr. Matthias Jakob and Karen Prezelj, who will be formally introduced prior to their presentations. RDEK Engineering Technician Kara Zandbergen, Engineering Services Manager Brian Funke, the RDEK's Communications Team, Larry Duchek and Nathan Siemens, and Protective Services Manager Fiona Durkle and Sean Tomlin, and we're all coming to you here via Zoom. There will be time for questions and answers once all of the presentations have been wrapped up. You can ask a question at any time by clicking on the Q&A icon from the menu at the bottom of your screen. Then simply type in your question. While you can ask a question at any time, we will not be answering questions until all the presentations have been wrapped up. We'll work through as many of the questions as we can. However, we do need to conclude the session by 8:55 p.m. As we want to leave as much time as possible on the agenda for information sharing in the Q&A portion, I'm not going to spend any time, any extra time. We're just going to move right into the first presentation with Kara Zandbergen. Who is the RDEK's engineering technician and will be the lead on the Fairmont debris flow mitigation project. Kara has been a member of the RDEK's engineering services team for several years and has worked extensively on flood-related projects, including Fairmont Creek debris flow mitigation, Hill Road Dike, and other projects, and also one of our incident commanders this spring, where you may have seen her working on the debris flow following the situation in Fairmont on May 31st. Kara will provide an overview of the Fairmont flood and landslide service area. And with that, I would ask that you please welcome Kara Zandbergen. Thank you, Kara.
I'm having problems with my microphone.
I'll be able to move your slides for you, Kara.
No, I'm looking at my mic.
You are unmuted, Kara. We can hear you through the system mic.
Okay, thank you. Hi, everyone. Thank you for joining us this evening. Well, the focus of this information meeting is the Cold Spring Creek assessment and mitigation project. I wanted to take the opportunity for just a few minutes to speak about a few different topics related to the Fairmont flood and landslide service area. I will speak, sorry, next slide, Larry. I'll speak briefly. I'll give you a quick history of the debris flows in the area. I'll talk about the service area boundary and the services that the service area provides. Quick talk about the financial information. Then I'll talk briefly about the mitigation that's been done on Fairmont Creek so far, and then I'll get into the Cold Spring Creek mitigation project. Next slide. So as we all know now, most of the community of Fairmont is built on the debris flow fans of Fairmont and Cold Spring Creeks. Sometimes we forget how the land under our feet was formed when there was large periods of time between events, but we have had some reminders in the last several years. In 2012, we had a fairly large debris flow event on Fairmont Creek. This was a big reminder for everyone of the hazard. Very thankfully, it was a reminder that came with some property damage, but no loss of life. In 2013, we had smaller events on both creeks, and then again in 2019, and most recently, we had our May 31st event this year. Next slide, please. So prior to the 2012 and 2013 events, there were already two small service areas in place, one for each creek. You can see on the map, those are the colored areas. After the events, it was apparent that the debris flows on Fairmont and Cold Spring Creek impacted the entire community and not just the properties immediately adjacent to the creek. So we recognized the need for a larger, more community-wide service area. And after extensive community consultation, the new Fairmont flood and landslide service area was established in 2014. So the new area the new service area includes the entire area in the dark blue line on the map. And I know there are areas where it seems like it's areas that possibly shouldn't be included, and they were included because they're part of the community of Fairmont. And it was apparent that in a debris flow event, there's impacts to roads, to infrastructure, to businesses, to potentially water and sewer, not just to residences. And that was the rationale for the large surface area that we have. Next slide, please. So we wanted to discuss some of the services that are provided by the Fairmont Flood and Landslide Service Area. So we conduct regular inspections of the mitigation structures, and we report on them to the province. We do maintenance, debris removal from the containment bases, and any other repairs that are required, like riprap repairs or vegetation control. We apply for grants so we can move forward with our larger mitigation projects. We plan and manage these projects. We coordinate the response to the events that are occurring on our creeks, and we communicate with our stakeholders. Next slide, please. So the current service area tax averages roughly $70 per property per year, and this is what we use to pay for all of the services described previously. So in addition to our regular maintenance services, we need to build up reserves for the future projects that we know will be required on both creeks. We seek funding for all of our projects, and we've been very successful in the past. Most of our funding programs require that the local government provides a percentage of the total project cost. It can be anywhere from, nothing. We've had projects that are 100% funded, up to 33% is not uncommon. When we apply for these projects, we also need to show that we have the resources to maintain the structures we build. So the maintenance will include the inspections and reporting, repairs, debris removal that we've described previously. And if we can't show that we have the adequate funds to maintain the structures we build, we won't get the funding we need. So debris removal includes the debris that accumulates in small amounts over longer periods of time, and that's more maintenance type work. It also includes a large amounts of debris from events that we've experienced in the last few years. Our experience to date has been that the province, through Emergency Management BC, has provided some financial assistance during the events for debris removal, but not, they don't pay for all of it. We are responsible for the remainder as a service area. So to provide a bit of perspective on how much these events can add up, the cleanup and repairs from the May 31st event, by the time we're done, will cost roughly $600,000. We are still working with EMBC and Disaster Financial Assistance to determine how much they will be able to pay for this. But at this time, it's expected that the service area will be responsible for between $70,000 to $90,000 of that total. And as we build more debris flow and debris flow mitigation, as we build more debris flow mitigation infrastructure, and as events happen more frequently, the maintenance costs increase. And we know that we will be having more projects on both creeks. So what that comes to is that we'll be looking for a tax increase for the service area. It's something that we wanted to bring up during these meetings. We're expecting it to be more than 3 times the current rate, and we will be coming out to the community in a few months to talk about this in detail. There will be an opportunity at that time for property owners to provide input, and we do need the community to approve this increase before it can happen. I've given an amount of more than 3 times, and this is really rough. When we come back to you in a few months, we'll have an exact number, but we really just wanted to give you to give an idea of what kind of increase we would be looking at. Next slide, please. So while the focus of today's presentation is Cold Spring Creek and that project, I wanted to just talk really briefly about the work that we've already done on Fairmont Creek. So we had the large event in 2012 that we all know about. In 2013, we had hazard and risk assessment completed on that creek, and it came with suggestions for mitigation projects to reduce the hazard to the community. We moved forward with these recommendations as quickly as we were able to. We started in 2013, we did some repairs on the Marble Canyon area that was paid for by DFA. In 2015, we completed phase 1 of the mitigation, and that was widening the channel through the golf course and building berms to keep the debris within the channel. And between 2016, we worked on our phase 2 project, which was large debris basins and containment weirs upstream of the Fairmont Hot Springs Resort. We also installed a weather station at that time, and we were looking to use that weather station for an early warning system. So the phases on Fairmont Creek all work together to reduce the hazard to the community, and that's recognizing that we can never reduce it to zero. There will always be some remaining hazard, and we will have more projects on Fairmont Creek in the future also. Next slide, please. So moving on to the Cold Spring Creek project that we're currently working on right now. We had a hazard and risk assessment completed for Cold Spring Creek in 2015. In 2019, there was a debris event on the creek, and at that time we had the upper watershed assessed again by a geotechnical engineer. They gave recommendations for mitigation works on the creek, and the recommendations were based on both of these assessments. We used this information to apply for funding through UBCM's Community Emergency Preparedness Fund Structural Mitigation Program about a year ago in October 2019, and we were awarded the funding in early March of this year. So that was a funding amount of $750,000. We added $150,000 from the service area reserve to bring the total project budget to $900,000. Next slide, please. So we started right away to procure an engineer for the project. So we had a competitive request for a proposal process. The contract was awarded to McElhaney in May of this year. McElhaney had partnered up with BCG Engineering, and the team recommended that the hazard assessment for the creek be updated prior to beginning the design phase. The assessment was completed roughly a month ago, and noted that there is potential for large damaging debris flows on Cold Spring Creek. Next slide, please. So with this information and at the advice of our professionals, we adjusted the project to focus on mitigating the debris flow hazard rather than the debris flood hazard. And Dr. Jakob will explain the difference further in his presentation. We expanded the project budget by adding $475,000 of community works funds to our budget, bringing the total project budget for phase 1 to $1,375,000. We know now that this will be a phased project, and this is just phase 1 of 2 or more phases, and the remaining phases could reach a total of up to $11 million. That's a rough number at this time, but that is, again, kind of the order of magnitude that we're looking at for our Cold Spring Creek project. And that's all I have for now. Thank you.
Thank you, Kara. Our next presenter is Dr. Matthias Jakob, who spent time in Fairmont earlier this year completing a detailed hazard analysis on Cold Spring Creek. Dr. Jakob is a principal geoscientist with BCG Engineering. He is an internationally recognized specialist on the subject of geohazard and risk assessments, and one of Canada's leading experts in hazard and risk assessment of landslides, especially debris floods and debris flows. He has completed assessments in over 100 creeks in Canada, Chile, Argentina, Ecuador, Bolivia, and Austria. Since obtaining his PhD from the University of British Columbia over 20 years ago, Dr. Jakob has been a full-time consulting geoscientist who has earned a worldwide reputation for his research work and rigorous application of the scientific method in fieldwork. Through his efforts, professional practice guidelines for landslides and flooding have been substantially improved in British Columbia and are now being extended throughout Western Canada and internationally. Dr. Jakob is the author of numerous well-cited publications and book chapters and is the co-editor of the 2005 text Debris Flow Processes and Related Phenomena, for which he was awarded the Burwell Award of the Geological Society of America. And in 2016, Dr. Jakob was awarded the Thomas Roy Award from the Canadian Geotechnical Society for his many achievements in the field of engineering geology. So with that, I'd like to turn the mic over to the Zoom over to Dr. Jakob.
Many thanks, Director, for the kind introduction. As announced, I will be talking about the hazard assessment that was completed this summer and finished and sent in as a final report just a month ago. My work will detail, first of all, what kind of characteristics exist to make Cold Spring Creek what it is, namely a basin, a watershed that is subject to debris flows and debris floods. And I will spend a fair bit of time explaining what the two differences are between these. I will elaborate on the frequency magnitude analysis that we did in order to arrive at a reasonable answer to the question, how big and how frequent can these events become? And how frequent have they been in the past? I will then explain how these results were translated into a numerical model where we created an equivalent fluid of the real thing on our computers. Combine those as hazard maps that can be translated directly into policy. After that, my colleague Karen from McElhaney will be touching on the short-term and long-term mitigation measures. So let's start with looking at a steep creek watershed. Steep creeks are typically defined as those that have a 5% or steeper gradient. They emanate from the watershed. They can drain glaciers. They come from areas that are subject often to various forms of landslides. Then they debouch on a landform called an alluvial fan. Due to the sudden change in gradient, the flows spread out and often dump their debris that they've picked up on their way down from the mountains on these fans. As they dump their debris, channels often aggrade, and that's the term for sediment buildup in the channels. And when they do so, they lose confinement and often jump out of their beds in so-called avulsion channels. And these avulsion channels, of course, are unwanted because they often interfere with built infrastructure and homes. Now, there's a continuum of processes between floods, debris floods, and debris flows. And that continuum is essentially the addition of sediment to the water. In floods, you typically have very little, less than 1% sediment, most of which is suspended, which makes the water brown. Some of it is transported as bedload at the bottom of the river. For debris floods, the sediment transport rate increases dramatically, and you can entrain grains along the riverbed. Even the largest ones become mobilized. However, they still tumble and saltate along the bottom of the stream. The sediment concentration of debris floods can be perhaps 10–15%, depending on where it's coming from. Debris flows are no longer called a fluvial process, but a landslide process. And they resemble more liquid concrete with a sediment concentration of 50, sometimes up to 70%. So more sediment than water. Some other characteristics are that debris flows are very fast. They can exceed running speed. They result in discharges sometimes as high as 50 times for the equivalent return period than a flood. Their density is much higher. They can be almost as dense as the rocks they carry. And the that particular characteristics makes them carry rocks up to several meters in diameter. Their recognition, therefore, is very, very important, because if bridges, culverts, or other stream crossing infrastructure is designed for floods or debris floods rather than debris flows, that can lead to a lot of damage. Now let's switch back to the debris floods. Debris floods have inundation potential. However, inundation is typically with water and sediment at a fairly low flow depth. Debris floods are very well known for being highly erosive, and debris floods have in the past eroded banks, often up to 50 or 100 meters, such as what occurred in 2013 in floods in the town of Canmore on the Upper Bow River. You're probably familiar with some of those pictures. This is the lower basin that shows at the end of Cold Spring Creek, just as it flows into the Columbia River floodplain, where you can see brown water and granular sediment and some logging debris or some log debris. Then here you see a trail that crosses upstream of the ski area, or used to cross upstream of the ski area to the other side of Cold Spring Creek. And this was outflanked by erosion in the last event. Down here you see the reservoir at the Fan Apex that was completely filled in several events in the past 10 years by debris and had to be dug out. And you see muddy water flowing down the roads in various places where culvert capacity is exceeded. Now, the difference between debris floods and debris flows is best explained when we just look at a few movies, this one being from Arizona and occurred this year. What I'd like to point out is how quickly these events unfold. Small watersheds are very responsive when it comes to high intensity rainfall. In other words, it doesn't take a day or days for the water in the watersheds to accumulate, but it can take an hour or less. That's particularly relevant in watersheds like Cold Spring Creek that have a lot of bedrock. Water level can rise fairly quickly, and here you can see multiple streams that coalesce. And in the next slide, I will show you an example of a debris flow, which is a very, very different beast. And I would like you to be aware that the channel width here is about 20 meters, and the largest boulders being transported in this event are up to 6 meters. This is a creek channel called Illgraben. Graben is like gully in the Swiss Alps, and curiously it has the exact same watershed area as Fairmont Creek, and indeed shares very many characteristics of that watershed in terms of sediment supply. While the approaching mass here seems to be slow, it comes down at about 5 to 6 meters per second, which is roughly 25 kilometers an hour. Therefore, you would have to be a formidable sprinter to run away from this mass. The largest boulder that is about to fall over the weir here is 6 meters in diameter. And that gives you an appreciation of the tremendous impact forces that debris flows like these can have, but it also gives you an idea how easy it is for a liquid concrete mass like this, or resembling a liquid concrete mass, to transport very large boulders. And then last but not least, just a reminder of the Hotsprings Creek debris flow of 2012. These images have been taken after the debris flow have come through, but note the very large boulders and the interbedded large organic debris that is preferentially being deposited at the side of the river and having avulsed out of its channel. So there is a very well thought out method in doing these hazard and risk assessments. First of all, one needs to recognize what type of hazard one deals with. And that we can do by looking at the watershed characteristics, as well as looking at the sediments that we encounter in natural cross sections, as well as in testing, of which we were able to dig about 5 of them all over the fan. Then, with a variety of methods, that some of which I will explain, we can establish a frequency magnitude analysis, which answers the question how large and how frequent these events can become and have been in the past. Once we've solved that, and with our knowledge of the physics of such events, we can put data into our computers and create an equivalent fluid of the real thing that behaves just like a debris flow. However, just on the screens of our computers, and we don't have to run any physical models. From that modeling, we can derive particular hazard scenario maps, which show for each return period how debris floods or debris flows may behave. We can then combine all of these maps to create what we call a composite hazard map, which illustrates the hazard, meaning the probability of the events, as well as their intensity, proxied by their impact force. Second steps then, that we will work on later, are determining the consequences of these events to build infrastructure. However, this is not part of my presentation tonight. Cold Spring Creek has been studied and examined in the past. There has been a study by Clarke Geoscience and Tetra in 2015. And this is the map that some of you may have seen before. The authors did some test trenching along the creek channel and some watershed investigations. They then classified hazard much like we do by probability, which you can see here on the vertical axis, and volume of the events in the horizontal axis. And they concluded that there's a moderate hazard along the center line of the creek, the corridor of the creek, and avulsion paths of lower hazard along the southern and northern fringes of the fan. We updated this study, and as you may imagine, science has advanced. Unfortunately, the news are not good. Our hazard results are significantly different, i.e. Worse than those shown in the 2015 work. One of the first things we did is we obtained from the district LiDAR imagery, which is highly precise topography of the fan itself and the watershed. So what you see, all these little lines are contours, and all of you who are hikers or climbers are very familiar with contour maps. And they show a fairly steep upper fan. However, the fan does not end at the highway. It continues all the way down and interfingers with the Columbia River floodplain. And here you can see the meanders of Columbia River. Now you see some strange blobs or islands within the fan here, delineated by red, and on the southern and northern portions of the fan. These islands are remnants of glacial lacustrine terraces, which developed when the entire valley was a lake dammed by glaciers up to roughly 11,000 years ago. When these glaciers, the damming glaciers in the last ice age, disappeared, these lakes drained, probably catastrophically, and left behind these silty terraces that flank the entire Columbia River Valley on either side. The debris floods, debris flows that followed this event then scoured these terraces and connected the debris flow fan with the Columbia River floodplain, but left some remnants, this one on which the current graveyard is situated. We also hiked up the channel of Cold Spring Creek approximately 3 kilometers and visited several side slope landslides. What we discovered is that the channel itself is riddled by side slope landslide on both sides, which occur, as they are seen here, shallow, by undercutting of the creek as its stage goes up. It cuts the bottom of the slope, and then you have these shallow landslides discharging the sediment into the slope. Often they push the creek into the opposite side, which then triggers a landslide on that side. However, a close examination of the LiDAR precision topography revealed that the lower watershed is riddled with deep-seated large landslides, many of which are either inactive or what we call dormant. Dormant means exactly what the word says. They are sleepers, which under changing climate conditions, or if undercut by either fluvial processes or by anthropogenic interference, can reinitiate, thereby shedding more material into the creek. A very notable feature we identified is what we call now the Cold Spring landslide, which started way up here in the watershed and was rather deep-seated, so something like 70 meters deep, millions of cubic meters of debris. And it went not only to the creek, but as you can see in the next slide, crossed the creek. So here delineated in a blue dashed line is the Cold Spring landslide, and it was powerful and fast enough to run across the creek, damming the creek, causing upstream a landslide dam, and then very likely leading to debris flows either through the impact itself or through the sudden drainage of this impoundment upstream. The remnants of this impoundment are long gone upstream due to the high geomorphic activity of the watershed, which means lots of rockfall, lots of debris flows, lots of sediment movement. And these various symbols here, these are just observation points where we either did dendrochronology, which I describe later, or we noted fresh slides, or what we call here the ripples, which are compression features. As you may imagine, what happens when the landslide comes down, hits the opposite side, it compresses and creates little waves, much like if you have a tablecloth and you push it from both sides. We also noted during our first drive-through across the fan area, and I'm sure you're all very familiar with that, that the fan is riddled with large boulders, some of which have been used ornamentally in people's front and backyards. We compared the lithology, so the geologic makeup of these boulders, with the different geologies defined in the landslide, in the watershed, excuse me, and discovered that they must have come from the watershed itself. However, when you compare the caliber of boulders that have been moved in the 2020, 2019, or 2013 debris floods on Cold Spring, with the size of this boulder that I'm standing next to down here, it is clear that those events that you've witnessed in the recent past are clearly unable to move these large boulders. So that, of course, begs the question, how did they get there? And the only rational explanation, given that this is an alluvial fan and not a glacial deposit, is that they were moved by debris flows, much larger than what has been observed in historic time. There is, of course, precedence for that, and this is one of the most striking ones. This is a boulder field that was photographed in the small town of Montecito in Southern California, just south of the larger town of Santa Barbara. This is a very, very affluent community with numerous millionaires and multimillionaires living. And many of these boulders were, much like Cold Spring, used ornament. I will talk about this later because during the development of this town, which has been here for hundreds of years, these boulder lobes and boulder fields were pretty much ignored in the development and zoning. One other thing we did, and we are very grateful to the district and to Fairmont Hotsprings to facilitate that, because it is somewhat invasive. We were able to dig 5 test trenches down to approximately 4 meters deep. And these are for us a wonderful opportunity, not only to decide what kind of event occurred, but also to date these events. The what kind of event occurred is manifested in what we call the sedimentary stratigraphy. What that says is, if, for example, clasts, like you see here, this is maybe a 40 or 50 centimeter type clast, are within a smaller matrix, and the clasts are randomly oriented, and there's no gradation from large clasts to fine sediments to the top, this is clearly an indication of a debris flow. Interbedded in these debris flows, do we sometimes find layers of debris floods where clasts are imbricated? That means they're shingled and they've been moved by water rather than by debris flows, which is very high density flows. In between these separate layers, do we find what we call paleosols? These are ancient soil horizons that were covered by these debris flows. The lovely thing about these ancient soil horizons is that they have organic material in it. And using the carbon isotope 14, one is able to extract materials, even very small pieces in milligram weight, send them to a specialized laboratory that uses the decay of the isotope 14, carbon isotope 14, its half-time, and analyze the age of this soil horizon, which then provides a minimum date to the overlying debris flow units. Here in this soil horizon, we found 3 different dates, one about 400 years ago, one about 2,000 years ago, I'm rounding up, and one about 3,000 years ago. That gives us an idea of how often this particular location has been affected by debris flows and how thick these debris flows have been in the past. Another technique we use is dendrochronology, so the science of tree ring dating. The particular science that we use here is called dendrogeomorphology. And it is the science to use trees to decipher geomorphic, so land surface processes that have occurred in the past. It's a very elegant method, and we call it also an absolute dating method because we can determine the exact year of occurrence, unlike the radiocarbon dating, which typically gives us a range of, say, 50 or 100 years in which an event has occurred. The top right here, you see a cross-section of a tree that was cut down, not in this project, but another one. And you can see here in black, that's the impact scar where the tree was hit by a debris flow, much like this ponderosa pine where I'm busily taking a tree core. And here you can count the tree rings back until you get to that black scar tissue, and you know exactly the year in which it happened. Note there's another scar tissue right here, so this debris flow this tree has been affected by debris flow twice in its life, which we then abruptly ended by cutting it down. Here, this method does not kill the tree, and one obtains a core that one sands, and you can see a sample down here. This is approximately 20 centimeters long, and it shows the tree rings, sometimes some what we call traumatic resin tissue in between the layers that indicate the tree was stressed likely by debris flows. We also see dramatic reductions in growth. For example, in here you have over 1 millimeter or so, 20 years of growth, versus here these tree rings are maybe 1 year per millimeter. And these dramatic decreases in growth also tell us when the tree might have been impacted by debris flows. We repeated that over numerous trees, both in the channel and on the fan, and we're able to cartoon past debris flows that have happened. While this isn't precise, because we couldn't core every single tree on the fan and many already had been cut down, it gives us a pretty good idea of events that may have happened in the past few hundred years. We also noted that there were so-called boulder levees paralleling the creek in the lower watershed. By using a standard measuring tape and a stadia rod, we can measure the cross-section area that has been occupied by debris flows in the past. And if there's old impact-scarred trees on the side of the channel, we can not only tell how large the discharge was of a past event, but we can also tell when it occurred. And that, of course, feeds into this all-important frequency-magnitude relationship. When the cross-sections become too large for our measuring tape, we can go back to the precision topography and reconstitute the cross-sections of interest right on our computers and do the same exercise as I just explained. Now, when we take all of these pieces of the puzzle together, first, some empirical method that relate fan area to frequency magnitude, the dendrochronology, the radiocarbon dating, paired with some professional judgment, we can establish these so-called frequency magnitude curves. I'd like to explain those. The horizontal axis down here is the return period. You can translate that into annual probability by just taking 1 over the value you see. So if you take 1 over 10, that's a 10% chance of this event occurring in any given year. That would be a 1% chance in any year, and this would be a 0.1 chance in any given year. The vertical axis denotes the volume, the sediment volume of debris floods and debris flows. Just as a quick reminder, like a 10,000 cubic meter volume roughly equals 1,000 dump trucks of sediment. So if you imagine you have a 100,000 cubic meter debris flow, that's 10,000 dump trucks worth of debris. What I'd like to draw your attention to is that we have 2 different curves. We have a lower curve here in green, and these little box and whisker things, these are the error bars associated with our estimates, because our methods, while well thought out, cannot be precise. So nobody should tell you that debris flood could have 3,248.3 cubic meters. That would be well beyond the precision that we can offer. This green area here, these are the debris floods. Debris flows have a very different frequency magnitude relationship. We believe that debris floods, which are the events that you witnessed in the last 10 years, can occur with as little return period as a few years and up to 100 years. Getting bigger, of course, the rarer they become. Beyond a 100-year return period, and again, that's a 1% chance of it occurring in any given year, we switch to a different process that explains that gap between these 2 curves, and that is the debris flow process. The different colored lines here are just different techniques applied to either the dendrochronological data set or some other method we used. But you can see they coalesced fairly well, which means it gives us a fair bit of confidence that our estimates are not out to lunch, but are within reasonable error bounds. What this tells you then is you can go and ask the question, how big is a 100-year return period debris flow? And you go up the axis, find the curve, and read over here and see that this is 20, 30, 40, 50,000, perhaps 60,000 cubic meters in volume. Now, there is a few other things that are important looking into the future. You've all heard about the effects of climate change, and they're no longer something that happens in the future. They are occurring now. I'm sure you hear time after time things like the 10 warmest years ever measured on Earth have been actually in the 10 last years. This is not a statistical coincidence. This clearly signals human interference. Same thing with Arctic sea ice. Yet again, this year we broke the record for the lowest Arctic sea ice. Take glacial melt. Glacial melt is rampant throughout the world, And there is papers that forecast that most glaciers, mountain glaciers in British Columbia, will have disappeared by the end of the century. We have by now put so much carbon dioxide and other greenhouse gases in the atmosphere that we've raised the temperature to what we have not seen for roughly 100 to 200,000 years. By mid-century, we will be at a point having temperatures that we have not seen for maybe 3 million years. And by the end of the century, by perhaps 10 or more million years. Now, the time of human sedentary habitation, in other words, when we went from a nomadic lifestyle to one where we dwelled in cities and villages and so on, is the last 10,000 years, the Holocene era, in which climate was very well behaved, despite the little ice age that occurred from about 1500 to 1850. It was a very smooth ride. That is no longer the case. Now, question is, why am I telling you that? Well, there are some direct applications of that message to our watershed. One thing is that a warmer atmosphere can contain more water. There's an old law, old meaning it's almost 100 years old, invented by two physicists, a German and a French, I believe. One was called Clausius, the other one Clovechok, and they discovered through experiments that with 1 degree Celsius temperature increase, any air column or air volume can contain 7% more water. So if you imagine you warm up a piece of atmosphere by 3 degrees Celsius, that then would hold 21% more water. And indeed, the most sophisticated climate models now show that this simple rule holds fairly well. There's exceptions. In the tropics, there's a thing called the super Clausius-Clapeyron relationship, which means a doubling of that 7% to 14% per degree Celsius. For the area of our interest, we can expect by the end of the century, maybe a 100 to 150% increase in high intensity rainfall frequency, meaning a doubling or more of highly intensive events. In central British Columbia, that's a lot more dramatic. However, we also, and that's the right-hand graph, that looks at the intensity itself. The left-hand graph is the frequency of occurrence of high-intensity precipitation. The right-hand graph shows the magnitude of the change. And what it tells us, and that is very much in line with this Clausius-Clapeyron relationship, that by the end of the century, we can expect something like 20 to perhaps 35% increase in the volume of high-intensity rainfall. Now, if you take more frequent and higher intensive rainfalls, which are, of course, distributed differently in different seasons together, that means, without doubt, that debris floods and debris flows will become both more frequent and of a larger magnitude. And that's not good news. There's another thing that plays a role that is directly associated with climate change, and that is of permafrost. Permafrost means perennially frozen ground. And that does not imply that it is frozen from the very top downwards. Nope, there is what is called an active layer that unfreezes seasonally, i.e. in the summer. What you see on the right-hand side is part of a global permafrost map that indicates which areas in fairly large pixels are covered by permafrost or underlain by permafrost. And you can see that the upper watersheds of Cold Spring Creek and Hot Spring Creek are indeed underlined by permafrost. What does that mean? Well, every rock mass is jointed. These joints are natural ingresses for water, either through snowmelt or rain. As that water infiltrates into the joints, it goes to below the active layer that unfreezes seasonally and refreezes. That refreezing does a number of things. One is the thermal expansion of ice, which is 9%, loosens the rock itself. However, as long as the ice remains in the permafrost zone, it acts like a glue, like a cohesive agent that does not allow rockfall to occur, or at least significantly hampers rockfall. With climate change, these permafrost underlain areas are degrading. So the active layer becomes thicker, and what has been held together by ice no longer is. The left-hand image here is a rock avalanche that occurred north of Whistler just last year. And we strongly suspect that this particular rock avalanche had something to do with more and more worms ingressing into these rock masses by thermal conductivity, thereby releasing the ice that held these rock masses together and now collapsing. This isn't the only large rock avalanche that occurred in southern BC, but there have been 4 or 5 over the last 10 years, which is at a frequency that has not been observed so far. Of course, hinting that climate change is playing an important role here. So if you look obliquely, this is a Google Earth image, over to Cold Spring here on the left and the Hot Spring watershed on the right side, and you imagine that the lower limit of permafrost is this yellow line, it creeps up year after year as with the greenhouse gas emission, global temperatures increase. With this creeping up of the lower limit of alpine permafrost and the degrading of its permafrost, we will expect and we will see more and more rock falls and rock slides that detach along rock discontinuities, thereby feeding more material to the digestive system, if you will, of these creeks. So we have a number of unpleasant consequences of climate change interacting here. One is higher frequency of intense precipitation. Second, more intensity packed into these events. Thirdly, mountain permafrost degradation. And fourth, due to the drying trend in the summer, in between big storms, the stress on the forest will increase either through beetle infestations or just drought stress, which means that the forested portions of these watersheds will become more susceptible to forest fires. And once these places have burned, they are ever more susceptible to debris floods and debris flow. Now, taking all this knowledge we've gathered together, we then can look at numerically modeling debris floods and debris flows. Again, to gain confidence and making sure that there's not a model aberration that we should not trust, we use 2 numerical models that have very different physics. This particular model looks at the susceptibility for debris flows and debris floods, and it clearly shows that both watersheds, and that's not a surprise to us, are in fact susceptible to debris flows. It also indicates, though, that if a debris flow were to occur, it wouldn't stop up here in the channel, but it would run all the way down to the Columbia River floodplain and distribute over the fan. So that was a screening level exercise, but then we went to a more sophisticated computational fluid dynamics model called Flow2D. It tells us which areas are inundated, how thick the flow flows, and how fast it is. So I'll give you 2 examples here. This is the low end of the spectrum we look at. This is a 3 to 10 year return period debris flood. So the garden variety debris flood that you've seen over the last few years. What it shows, and here's the fan apex, here's the highway, down here's the Columbia River floodplain. It shows that all of these events overcome the capacity of the culverts, spill out of the channel, but the water flow is quite shallow. It's a few centimeters to maybe half a meter in more depressed areas, and of course in the creek channel itself. They're also not particularly fast. Where the creek jumps out of its channel, it's slow walking speed, where it's within the channel, it's a brisk walk, but still not a jog or a run yet. An event of this magnitude has roughly 2 cubic meters per second, which means 2,000 liters per second rushing through a cross section. And the total sediment volume transported past the fan apex, which is up here in a given event, would be approximately 4,000 cubic meters. So 400 truckloads, give or take. And the expression of that is what you've seen before. However, now when you go to a very rare debris flow, so one that has a 0.3 to 0.1% chance of occurring in any given year, and keep in mind, you have to multiply that by your life expectancy to get a probability of it occurring in your lifetime, which of course is significantly higher than the 0.3 to 0.1%. Then you get this result. So here, again, color-coded, you can already see, compared to the last slide, that I'll just toggle back a few times, that a much larger area is inundated by debris, that the debris flows reach all the way down to the Columbia River floodplain. The flow depths are dramatically higher, with large portions of the, what I call the upper fan upstream of the highway, getting up to 1.9 or 2 meters flow depth, so taller than most people. And the flow velocities can reach somewhere between 3 and 6 meters per second, within the channel perhaps even 10 meters per second. And keep in mind that the fastest people on Earth roughly run 10 meters per second. So that's something that one cannot run away from. Also, the peak discharge of this event is 260 cubic meters per second approximately, which is over 100 times larger than a debris flood that occurs at a 3 to 10 year return period. And the sediment volume of 76,000 cubic meter, of course, is orders of magnitude larger than the debris floods. So a completely different beast. And you have indeed witnessed one of those. This is the 2012 debris flow, on Fairmont Creek, which had a volume of approximately 64,000 cubic meters, and which created millions of dollars worth of damage. Now, we were able to model these debris flows for each of the return periods we were interested in, 3 to 10, the 10 to 30, the 30 to 100, 100 to 300, and so on, all the way to the 1,000 to 3,000 year return period. These return period classes are somewhat enshrined in guidelines that have been developed by the Association of Professional Engineers and Geoscientists of British Columbia. And once again, you can see dramatically the differences between these shallow debris floods and these deep, fast, and very destructive debris flows that happen more rarely, but they do occur. I'd just like to go back to that example earlier that I talked about in Montecito, California, this very affluent community at the foot of a moderate-sized mountain range here, which is not even half the height of what we see at Cold Spring. The watersheds upstream here were bereft of their vegetation during a forest fire that occurred in December of the preceding year. And curiously enough, one of these creeks here, this one is in fact called Cold Spring Creek. The depletion of these watersheds from their vegetation in combination with a storm that occurred on January 9th led to vast debris flows that inundated a great portion of these towns and destroyed numerous buildings. Unfortunately, the debris flow was of such magnitude that 23 lives were lost. I have no intention of scaring anybody that is participating in this presentation, but I'd like to give you an honest appraisal of the type of debris flow damage that could occur, even though that is really hard to wrap one's head around, that a building like this could be a building on Fairmont Hot Springs, on either Hot Springs or Cold Springs Creek. But it is, while rare, it is physically feasible for those events to occur. What do we do with this information then? Well, we have a pretty good idea as to what kind of damage is created by these debris flows. It is kinetic energy that can be expressed as the flow velocity squared and the flow depths. So the flow velocity squared is very important. Any martial artist knows that if you hit somebody twice as fast, you hit them 4 times as hard. And the same, of course, goes true when you hit an obstacle with your vehicle. If you go twice as fast, you hit it 4 times as hard, given that the vehicle always has the same mass. Now, using that information, we then can classify impact force in classes from minor all the way to total destruction. And given that our numerical model outputs both the flow velocity and the flow depth, we can classify zones on alluvial fans by their destructiveness. And that's what we did. So what you're looking at here is an intensity map where we multiplied flow velocity squared times the depth, and we added, to make it even more realistic to resemble an impact force, the density of the flows, which in the case of debris flows can be more than 2,000 kilogram per cubic meter. So twice the weight of water. And what you see here is that large parts of the upper fan and underneath there are quite a few buildings are subject to red, which means very high impact forces for this extreme event. This is the 1,000 to 3,000 year return period event. And these impact forces would be strong enough to truly destroy buildings, much like you've seen these horrific photographs from Montecito. In the orange zone, the impact forces are somewhat milder, but still enough to cause major structural damage. While in the yellow zones, the impact forces are milder, and there more nuisance damage would be expected, and the building would probably survive and could be reconstructed or repaired at a much lower cost. We then take all of these model components and create what is called a composite hazard map. So we use every one of these individual return periods, combine it, and then multiply it by the frequency at which a certain zone is being inundated. What the red zone means is an area that is inundated often, and it is inundated by destructive debris flows. Orange is less often and less intensity, and yellow lesser yet. That, of course, translates into red zones having a high chance of fatalities should these events occur. The orange zone, a moderate chance of fatalities, and yellow, low chance of fatality. So let me conclude then. Cold Spring Creek, and I hate to be the messenger of bad news, but don't shoot the messenger. It is subject to debris floods and debris flows, which occur at different return periods. These hazards and risks that we looked at are substantially higher than have been believed in the 2015 studies. We've noted through our numerical modeling that debris flows may impact much larger areas and would be capable of causing fatalities. There's other studies planned to determine just what the life loss risk is, and that allows us to optimize mitigation measures to reduce life loss risk as much as possible with the funds we have. That goes hand in hand with an option analysis where we compare the different types of debris flow mitigation measures that are possible, and then try to pick the best ones that not only reduce life loss risk, but also economic risks associated with loss of property, impact to homes, infrastructure impacts, loss of egress and access, and so on. Last but not least, we're working currently on a proposal to develop a debris flow warning system, which is weather-based, which means that well before a storm attacks or reaches the area of interest, that we can tell whether or not the storm will result in debris floods or debris flows, and how much sediment could be moved. That pretty much concludes my presentation, and I'll hand it over to Karen, who will enlighten you about the ideas and plans for short-term and long-term mitigation. And I'll be more than happy to answer questions after her presentation when the floor gets opened.
Thank you, Dr. Jakob. Our next presenter is Kara Prezelj. Karen is a civil and hydrotechnical engineer with McElhaney. She's based in their Fernie office and works across the East Kootenay. She brings local experience and practical understanding to her projects. Karen specializes in all components of river flood mitigation, including river hydrology, hydrological modeling, hazard mapping, design and construction of mitigation measures, and emergency flood support. Her recent work in the area includes dike improvements on the Elk River in Fernie, flood mapping on Joseph Creek in Cranbrook, and emergency flood support on Windermere Creek in the Windermere Bank, armoring on the Elk River in Sparwood, and Kakado, and hydrotechnical culvert design on Fraulein Creek near Spillamachine. She also has significant experience working in southern Alberta on flood mitigation work following the 2013 flood. And her presentation today will focus primarily on the plans for phase 1 of the Cold Spring Creek debris flow mitigation project. So Karen, please go ahead with your presentation. Thank you.
All right, yeah, thank you. Thanks for the introduction. Yeah, so as mentioned, I'll be discussing our proposed mitigation against debris flows on Cold Spring Creek. And again, focusing on phase 1, which is what we're working on right now. So for phase 1, we're planning a flexible debris net. Right, so flexible debris nets capture and retain rock, trees, and other debris during a debris flow event. These systems function similar to a dam, but with much lower construction and maintenance costs. The nets will fill with debris after a major event, as shown in this photo, and will be cleaned out by crews coordinated by the regional district. All right, as you can see in the attached aerial image, the net will be located upstream of the community and upstream of the Hotsprings Resort Reservoir and the Poets Hiking Trail. It's going to span across the entire Cold Spring Creek Valley. The net we're proposing will be 40 meters wide by 6 meters high, and it's expected to retain around 20,000 cubic meters of debris. We'll be constructing an access road from the Fairmont Hot Springs Resort Reservoir, where there's an existing access road, to the upstream side of the proposed debris net. This will allow for construction access, as well as maintenance and cleanout access once the project's complete. This access road will also provide recreational and wildlife passage over the debris net once the project's completed. All right, here's our proposed timeline for this project. We've recently completed the hazard assessment of Cold Spring Creek, which was just presented on by Dr. Jakob. We're currently working on the design of the debris net. The construction of this debris net is planned for next summer in 2021. And like discussed previously, we're considering this proposed debris net to be phase 1 of debris flow mitigation on Cold Spring Creek. In the future, the regional district hopes to build additional debris flow mitigation as funding becomes available. All right, before I wrap up, I wanted to highlight a very similar debris net that was installed in Canmore, Alberta after the 2013 flood. It was installed on Cougar Creek, which is a creek with similar debris flow hazard, also located above a developed community. This installed net, as shown in the picture, has the same dimensions as the proposed Cold Spring Creek net, 40 meters wide and 6 meters tall, and it was designed to hold back a similar volume of debris. All right, that's my presentation. Thanks for listening.
Thank you, Karen. So that concludes our formal presentations this evening, and we'll now move into the Q&A portion of the meeting. And just to remind you, if you have a question, please go to the bottom of your screen and click on the Q&A icon and type your question in there. And we'll open up the that Q&A session right now. It looks like we have one. I'm going to have Laurie can moderate the questions, or would you like me to do that, Laurie?
No, that's okay. I'm happy to moderate the question. So our first question is, does the tax rate reflect parcel size? For example, does Fairmont Resort pay more? They have a large land base in both creek basins. And I do have the answer to that question if you'd like me to share it, Director Clovechok.
Sure, that'd be great.
The tax base is based on assessed value. So large properties like the resort would pay a larger amount than individual homes. Also, commercial properties are taxed at a higher rate than residential. And our next question, I believe, will be directed either, well, actually, it could be directed to Karen, Kara, or perhaps Dr. Jakob. The question is, how well does the mitigation procedure proposed in phase 1 fit in with Dr. Jakob's estimations and science?
Do you want me to take this?
Sure.
Yeah.
Sure, I can elaborate here.
Yeah, so our proposed debris net for phase 1 is estimated to hold back 20,000 cubic meters of debris. Dr. Jakob's estimation for debris flows are around 60,000 cubic meters to 100,000 cubic meters, depending on the return period. So that's why this is phase 1 of the proposed debris flow mitigation. So we hope to reach those volumes in the future phases.
Thank you. So we have another question here. The rain event in May this year was significant. This one is for you, Dr. Jakob. I should have said that first. I'll repeat the beginning. The rain event in May this year was significant, but not extreme. Would a similar rain event cause a debris flow or another similar debris flood?
It's a good question. So a rain event of the same magnitude would likely cause a debris flood of similar magnitude. However, it does depend on the prevailing snowpack and the snow water equivalent in the watershed. So imagine the same rain event occurs, but there's half a meter of very wet snow. And let's assume that the rain event goes right to the mountain peaks. In other words, there's no snowfall. And let's perhaps assume, so I'm painting the worst case scenario, that the remaining snow is very saturated. So it has a very high density. In other words, it does no longer work as a sponge, but transmits its water directly down to the floor and melts at the same time. Then the outcome could be a lot more extreme than if there were a rainfall event with, say, 30 millimeters without any snow. I'm also happy to answer Mr. Smithstad's question of have there been circumstances to test the efficiency or efficacy of the Cougar Creek Kenmore net.
Sure, I was actually going to direct that one to you next, so jump on in.
I'm jumping the gun. So the short answer is no. The net was built very quickly in order to be protected from the next event. Unfortunately, Cougar Creek had a debris flood in 2012. Then $3 million were spent on mitigation, and that $3 million was completely wasted, unfortunately, in the year after, in 2013, which essentially destroyed all that previous mitigation. So having witnessed 2 consecutive events, the town of Kenmore did the right thing and very quickly built such net. But then as the statistical gamble goes, it was never stressed by a true event. The net has now been taken down just as a follow-up to that and is being replaced by a $40 million structure at the same location.
Thank you. Our next question is for Kara Zandbergen. And the question is, are there plans to clean out the lower catch basins above the Riverside Golf Course maintenance shops as was done on the upper basin by the Poet Creek Trailhead? Are there other catch basins, example by the highway?
Yes, we are planning to clean that out in the next month, actually. As to are there other catch basins, there is a small one between the Riverside maintenance pond and the highway. We will try to clean that out. It will depend on a few factors, like presence of fish and whatnot. But the main one down by the pond will be cleaned out in the next month.
The next question is either for Karen or for Kara. I'll start first maybe with Karen, and Kara, you can add if it should have been directed to you. What mitigation procedures beyond flexible nets are being considered for the estimated $11 million of phase 2, and what level of mitigation will they be designed to from a volume perspective?
Sure, yeah, I can answer that. So we're looking at hopefully building a concrete check dam for phase 2, which has been installed. There's been a number of them installed, mostly on the Sea to Sky Highway area in BC. So that would be Yeah, it's like similar to a concrete dam, but with an opening in the middle with an area for clear water flows to pass through. Yeah, we may also consider additional nets if future funding doesn't allow us to construct a large check dam all at once. Do you want to add anything to that, Kara, or is that?
I guess the only thing I would have to add to that is that perhaps during the options analysis, we may come upon more solutions.
Great.
The next question I will direct to you, Kara. Just, I know you did touch on it in your presentation, and perhaps you can just reiterate it and provide maybe some more specifics. Dr. Jakob noted in the upper basin trap that it was filled over it was previously filled spanning the past 10 years in his review in 2020. When was the last time this was emptied by RDEK maintenance?
Last summer, actually, in 2019.
And the next question is, does the 3 times cover all phases or just the first phase? So I think that is in reference to the tax increase that you mentioned in the beginning of your presentation earlier this evening.
So the 3 times, like I mentioned in my presentation, is very rough right now. And our intent is that it will cover hopefully all phases, if not all. We would rather come out once and cover all phases than have to keep coming back to the community over and over again.
Okay, thank you for that. That covers all of the questions that we currently have in the queue. Perhaps Director Clovechok, if you have a few closing comments that you would like to share, and just to provide some information on how people can continue to stay informed about the project. And if we do have any additional questions that come in, we'll maybe take those quickly once you've wrapped up.
Great. Thank you, Laurie. And thank you to each of our presenters very much for joining us this evening and sharing this important information with the community. And thank you everyone from the community who has chosen to join us in Zoom this evening. We felt that it was really important to get this information out to the community, and we're really grateful to the panel of experts that we've had at our disposal this evening to answer all of the questions. Kara is our project lead, and as things are just getting underway, she and our RDEK staff are going to be available to answer all your questions as we move through the project. And all of the project information will be available on the project page at engage.rdek.bc.ca/debris. That website again is engage.rdek.bc.ca/debris. And my contact information and Kara's contact information is available on that page as well. So please don't hesitate to forward your questions if you have any additional questions. And I see there's a couple that are just popping up now, and we'll get to those right away. But there will be a Q&A section on the page, on the engage.rdek.bca.ca page, that you can submit, because if you're anything like me, we're going to close this Zoom meeting and you're going to think of a question that you should have asked. So this is not your only time to get information. And I'd also like to encourage you, if you haven't already done so, to make sure that you sign up for the community notifications and the community emails that Laurie and Nathan do such a brilliant job of getting out to us by going onto the RDEK website. That's rdek.bc.ca. I apologize for all the dots and all the website information, but it is important. And if you register for those emails, you'll be sure to get the most current and timely information on this project. So with that, I think we'll just take these couple of questions here, and then I'll have some thank yous.
So the next question is, will the 3 times tax increase be in place for perpetuity or until costs are covered? And I believe our engineering services manager, Brian Funke, will be taking this one.
So we're very early in determining costs to finance the 1 to 3 projects. Well, maximum, minimum of 2, probably 3 projects. So we'll be working on that this winter and leading up to some sort of a community assent process in 2021. So difficult to answer that right now, but typically we borrow for periods of anywhere from 15 to 25 years. So along with the capital cost to build these projects, there is maintenance costs as well that Kara highlighted previously. So I know I'm not answering the question right now, but we have quite a bit of work yet to do to come up with what costs will be beyond that, say, 10 to 15 years.
Thank you, Manager Funke. And the last question is just how many viewers were there this evening? And the number that of viewers that we had, there were some people popping in and out, but the safest number I can give you is 18.
Okay, thank you, Larry. And it's important to note too that this session has been recorded, as was much of this afternoon's, and they'll also be available on the engage.rdek.bc.ca. So please encourage any of your neighbors that weren't able to attend this evening or this afternoon's sessions to go onto that website and take the time to view the presentations, because it's very, very informative. And with that, I'd like to thank the RDEK staff for all the work that they've put into this session this evening and this afternoon, and their work in putting together the meetings and also the content. So thank you, everyone. As is typical with Zoom, these things end quite abruptly. So it's not because we're being rude, it's just how the technology works. So have a great evening, stay safe, and please stay tuned to project updates as they come forward. Thank you.
Thank you. It was a pleasure talking to everybody.